Thank you very much for this excellent opportunity to present our work. I will discuss binary choice with asymmetric loss in a data-rich environment. Algorithms are used more and more frequently for decision-making in different settings, and there is a growing concern of the problem of algorithmic discrimination. For example, algorithms are used to help judges in making bail decisions in criminal justice. And it has been reported that an algorithm called Compass that is used in several states tends to discriminate Black people against white people. So the algorithm predicts high recidivist risk scores for Black people 2 times more frequently by mistake compared to white defendants. In healthcare, algorithms are used to assess health risks. And it has been reported that an algorithm that affects millions of Black people tends to underestimate health risks for Black patients. Another famous example is the resume screening software. Amazon has developed an algorithm that helps to screen thousands and hundreds of thousands of resumes. And they discovered soon that the algorithm tends to favor men for technical jobs. And there are more examples of algorithmic discrimination, for example, in loan approval, ad delivery, and we also have the search engine bias. So the potential of machine learning algorithms to reproduce and even reinforce existing discrimination in the society has been of great concern recently. In addition, it has been recognized in economics going back at least to the Nobel Prize winner, Clive Granger, that the upside gains and the downside risks of many economic decisions are not symmetric. So the question that we ask in this paper is, how do we adjust machine learning classification algorithms for asymmetric losses and preferences? For example, we may want to control false positive or false negative mistakes across different groups, like Black and white, male and female. And more generally, we may want to make decisions based on economic costs and benefits considerations. So some notations, we are interested in making binary decisions or binary choices. We have some target variable y that is binary, takes only 2 values, for example, recidivist or non-recidivist. And we have some p covariates of individual, and the binary decision or prediction or choice is simply a function from the space of covariates to the binary decision -1 or 1. And we measure the quality of these binary decisions using some loss function. So the loss function tells us what are the costs for making mistakes or incorrect decisions. For example, putting someone who would not become a recidivist in jail. And also what are the benefits of making the correct decisions. And our objective here is to find a binary decision rule such that the expected value of the loss function, the so-called risk function, would be as small as possible. So if you talk about the binary classification that is most often used in practice, here the loss function is extremely simple. And we suffer 1 point of loss if you make a mistake. So if you put someone who would not become a recidivist in jail, we suffer a loss of 1 point. If we release someone who would become a recidivist, we would also suffer 1 point. If you make the correct decision, then there are no losses. And then there are also no benefits. So this is a quite unrealistic example of the loss function if you talk about the real life decisions. And for example, we may want to have a loss function that pays different attention towards different groups of individuals. So if you find that the algorithm discriminates a certain group of individuals, we may want to make this group a protected group. And we may want to adjust our losses so that if the algorithm makes a mistake for the protected group, it suffers higher losses. And more generally, we can also have different losses for making false positive and false negative mistakes. So false positive and false negative mistakes have very different implications in criminal justice. For example, releasing someone who commits a crime is something very different from putting someone who is innocent in and would not commit any crime in jail. And these false positive and false negative mistakes can also be different for different groups of individuals if you want to reduce the different treatment of the two groups of individuals. And more generally, we argue that the decision maker has to specify explicitly the preferences, the costs and benefits of decisions in different states of the world. So there are 4 possible outcomes. We can make the prediction, for example, that the individual would become a recidivist or not. And then there are 2 actual states of the world, one in which the individual would become a recidivist and another where the individual would not become a recidivist. And so depending on the state of the world, we have different losses. So for example, if you predict that someone would become a recidivist and this actually happens, then we have some economic benefits of detention, and we have also to pay for keeping this individual in jail. And on the other hand, if we predict that someone would not become a recidivist, but the individual becomes a recidivist and commits a crime, then we have some economic costs of recidivism. So the decision maker has to think carefully about all these economic costs and benefits, all these trade-offs, and also asymmetries along different dimensions, like the race, gender, and so on. And then once we have these loss functions specified in this table for 4 different states of the world, then we would need to adjust the machine learning algorithms by some weights. So we have to compute some weight Wi for individual I with the actual outcome yi and some functions a and b applied to covariates xi, where a and b are computed from the loss function. So for example, when we are using the logistic regression for classification, or more generally when we use boosting algorithms, we want to maximize this logistic log likelihood function over a set of linear decision rules, or more generally over some functional space. And with our approach, what we would need to do, we would need to add some weights to this objective function. So we would need to reweight the objective function to take into account preferences or losses of the decision maker. And we would do classification based on this objective function. Similarly, if you talk about the support vector machines or deep learning, we often use this objective function with some additional regularization. And with our methodology, we would need to add weights to this objective function that would adjust for asymmetric preferences and losses. So in the last part of the talk, I would like to discuss the empirical illustration for racial bias and recidivism. So the cost of prisons has skyrocketed recently. For instance, 30 years ago, the state of California has spent only 3% of its state federal budget on prisons and 10% on higher education. These days, the numbers are 11% on prisons and 7.5% on higher education. Also, there are more than 10 million people arrested each year in the US, according to the FBI statistics. And after the individual is arrested, there is a bail decision to be made by a judge based on the risk of recidivism. And there are lots of asymmetries here. So we have black and white defendants. We also have different types of misconduct. And also we have economic costs of crimes and benefits of detention. You look at the data set that was compiled by ProPublica. The data set covers over 11,000 of criminal defendants in the Broward County, Florida. So we have some demographics. For example, 80% of criminal defendants are male, 20% are female, 50% are African American. We also see the crime history and some other variables. And we also compile a table of economic costs and benefits of crime from a paper by Bauchman. So here we can see some examples. If a released individual commits a murder, then the costs for society are estimated over $10 million. If this is a minor offense like robbery, then we have costs of around $50,000. We also have some benefits of detention estimates, and we have individual costs. So, for example, there is a loss of income over $30,000 per year for the individual that spends some time in jail. And we have some public costs. For example, we have to pay over $30,000 to keep an individual in jail over 1 year. So these are the empirical results. What I would like to highlight here, we use deep learning and boosting, and in particular, the XGBoost algorithm. Standard implementation with symmetric loss functions. So this is this column and this column here. And we try our asymmetric approach based on the economic cost of crime and benefits of detention. So we have these results here. So what we can see from this table, we can see that there is around 13% cost reduction with our preference-based approach compared to the asymmetric deep learning approach. And also, if you compare these results to the logistic regression, then it can be seen that the deep learning can reduce a cost by 10% compared to the simple logistic regression. So deep learning and machine learning algorithms, they make a difference here. Also, if you want to equalize, for example, false positive and false negative mistakes, you can do that. So here, for example, in this first panel, we start in a situation where false positive mistakes for group 0, so this is the blue solid line, are higher compared to false positive mistakes in group 1. And we start introducing higher weights. So we pay higher price when we make mistake for group 0, and we see that at some point we can equalize these false positive mistakes for the two groups of individuals. And likewise, we can do this with other types of mistakes. So to conclude, machine learning classification algorithms are increasingly used in different life-changing decisions. For example, bail decisions, hiring, healthcare. And there is a growing concern that algorithms can reinforce existing biases in the society. At the same time, biased algorithms might be easier to fix and to regulate than biased people. And in this paper, we argue in favor of the preference-based approach that is based on the explicitly stated loss function that takes into account the economic costs and benefits of detention, for example, and that also takes into account preferences towards different groups of individuals. So this approach is extremely simple and computationally attractive, and we have lots of theoretical results in the paper.